Welcome to The Explainer. Today we're going to master one of the absolute foundational concepts in all of artificial intelligence. We're talking about logistic regression. Now, look, if you've ever wondered how computers actually make decisions, but you kind of break out in a cold sweat the second you see complex calculus, don't worry, you are in the exact right place. We're going to break down the mechanics, the intuition, and really the sheer elegance of how we mathematically predict the world around us. And we're going to do it in a way that is super intuitive, step by step, for absolute beginners.
So think about the really fundamental questions we want algorithms to answer for us every single day. How does your inbox actually know if an incoming email is spam or legitimate? Or even more critically, how does a medical model predict if a patient has a malignant tumor or if they're perfectly healthy? We're talking about a real-world problem here called binary classification. In these kinds of scenarios, the answer isn't a sliding scale or a range of numbers. It absolutely must be a 0 or a 1, a yes or a no, spam or not spam. The model gives us a probability, and then we simply draw a line in the sand, say right at 50%, to make our final yes or no decision based on exactly what side of the line that probability lands on.
Now, as humans, when we face a totally new problem, our first instinct is usually to just reach for a familiar tool, right? And in statistics, our absolute favorite, most familiar tool is just drawing a straight line. That's linear regression. And hey, linear regression is fantastic when you're predicting a continuous number, like if you want to predict a fluctuating house price based on square footage or someone's blood pressure, drawing a line of best fit through your data works beautifully. But when we transition over to a binary outcome, where the answer has to be an absolute category of 0 or 1, that familiar trusty straight line suddenly becomes a massive, spectacular problem.
Here's why. If you try to fit a straight line to binary data, that line is just going to keep extending endlessly in both directions. That means your model will actually start predicting impossible probabilities. It might literally tell you a patient has a negative 20% probability of having a disease, or 130% probability. Those are mathematically meaningless numbers, right? Probabilities absolutely must lie strictly between 0 and 1. Furthermore, a straight line is incredibly sensitive to outliers. A single weird data point way off to the side can pull the entire line completely off course, totally skewing your predictions and just utterly failing to capture any sort of clear, distinct categorical boundary.
And we see this exact issue pop up directly in real-world medical research. For instance, take this data from UC Davis Health on predicting coronary artery disease. They're tracking variables like a patient's age, but the final outcome they care about is strictly binary. You either have the disease or you don't. The researchers explicitly state it. Because the outcome is binary, they definitively have to abandon that straight line. They have to use logistic regression to make any actual sense of the data.
So enter the absolute hero of our story, the sigmoid function. Instead of predicting a straight line value, logistic regression predicts the probability of an event happening using this really majestic S-shaped curve. This S-shape is honestly a mathematical marvel. It's incredibly useful because it takes any real value on the horizontal axis, and I mean no matter how wildly negative or massively positive it is, and it gracefully squashes it into a neat, valid probability on the vertical axis, perfectly bound between 0 and 1.
Let's think about the physical behavior of this curve for a second. It acts almost like a mathematical trash compactor, but in a good way. You can feed it any messy combination of numbers, a patient's age, their weight, their blood pressure, and it beautifully compresses them all into one tidy probability. Right at the center, the probability sits perfectly at 50%. But as the inputs get extremely small or extremely large, the S-shape just flattens out, asymptotically hugging the bottom and top boundaries. It will literally never predict below 0% or spike above 100%. It just perfectly, elegantly solves that whole linear regression limitation. Okay, but you might be wondering what is actually happening mathematically behind that beautiful S-curve. To understand the engine here, we use something called log odds. Think about betting odds for a second. You know, the chance of something happening versus the chance of it not happening. By applying a very specific mathematical trick to those odds, we can actually still use our trusty old straight line math behind the scenes. Meanwhile, the final output that we actually see remains that beautiful, squashed S-curve.
If we take a quick peek under the hood at that UC Davis model, we see something truly amazing. The right side of the equation? It's just standard straight-line math. It's just adding up the patient's risk factors. The model forms this elegant bridge. It uses the simple, linear math we already know behind the scenes to capture the relationships, but then it generates those complex, strictly bounded probabilities on the outside. It's an incredibly elegant solution connecting what we know to exactly what we need.
All right, so we understand the shape of the curve now, and we get the intuitive math connecting the inputs to the outputs.
But that brings up a massive question. How does the computer actually optimize this? I mean, how does the algorithm learn to take our incredibly messy, real-world data, like scattered patient health records or thousands of totally random emails, and perfectly fit this smooth S-curve to it? Well, we need to look at the engine that actually drives this learning process.
To understand how it learns, we really have to talk about the optimization landscape. If we try to use traditional learning methods on our S-curve, the math creates a really bumpy, jagged landscape. Imagine trying to roll a ball down a hill to find the absolute lowest point, which, in machine learning, represents our least amount of error. But on this particular hill, it's full of fake bottoms and weird craters. The ball just gets stuck halfway down in a trap. The model simply cannot learn efficiently because it literally thinks it's hit the bottom when it actually hasn't.
So, to fix that, we use an entirely different engine called log loss. Log loss is absolutely brilliant because it heavily penalizes the model for being confident but wrong. Like if the model is 99% sure an email is safe but it's actually a nasty virus, log loss slaps it with a massive mathematical penalty. And this specific penalty actually smooths out all those craters we just talked about. It takes that bumpy hill and turns it into a perfectly smooth bowl for our ball to just roll right down.
Because we now have this perfectly smooth bowl, the algorithm can use a famous technique called gradient descent. Think of it literally like taking steps down a hill in the pitch dark. You just feel around for the downward slope with your foot and you take a step, repeating that until you finally reach the flat bottom. By finding the bottom of this smooth bowl, the computer systematically zeroes in on the exact mathematical weights that best fit our messy real-world data. And bam! Just like that, the curve is perfectly fitted. So, let's take all this really powerful theory and ground it right back in reality with that UC Davis health data. Now we can take any patient's data, like their sex, their weight, their age, feed it into our finished, trained S-curve, and get a completely clean probability out the other side. Using this trained model, they can explicitly compute that the probability of disease for an overweight 30-year-old man is precisely 21%. But for a 30-year-old overweight woman, it drops to 13%. We've successfully transformed raw, chaotic patient data into highly specific, actionable probabilities.
But honestly, here is the absolute superpower of logistic regression: interpretability. Look, today a lot of modern AI models are just total black boxes. They spit out an answer, but nobody actually knows exactly why. But because of the simple linear math hiding just under our S-curve, a doctor can look at this model and explicitly state males are about 14% more likely to have coronary artery disease. We can see exactly why the model made its decision, and in critical fields like healthcare, understanding that underlying reasoning is just as important as the final decision itself.
Because of this unmatched combination of well-calibrated probabilities and crystal-clear interpretability, logistic regression remains a totally foundational, trusted baseline across massive industries. In healthcare, it's out there driving medical diagnosis. In finance, it's determining credit scores and figuring out loan defaults. Human resources departments use it all the time to predict employee attrition. And even natural language processing relies on it heavily for spam and fraud detection. This simple mathematical squashing function is quietly powering major decisions all around you, every single day. So we started with the spectacular failures of drawing a straight line, and we found this incredibly elegant solution in the S-curve. We've seen exactly how transforming a linear concept creates a robust, highly intuitive engine capable of accurately classifying really complex human health and financial behaviors. So I'm going to leave you with this final thought to ponder. If a simple S-curve can so accurately parse the noise of our daily lives into such clear, precise probabilities, what else in our totally chaotic, unpredictable world is just waiting to be mathematically squashed? Thank you so much for exploring logistic regression with me today. Keep asking questions, and as always, keep learning.